Good afternoon, everyone. Welcome to doubt clearance session, or rather, problem solving session for week 9 on the course of regression analysis. I am Shreya, one of the TAs for this course, and today we'll be discussing some concepts which were already touched upon and explained thoroughly during week 9 lectures, and we'll solve a few hands-on problems to see how we can tackle or how we can implement these methods in the real world scenario. Okay, so without any further ado, let's get started. I hope you can see my screen. All right. So the first thing that we learned in the previous week and in this week was transformations of various types of variables and some sort of weighting to correct for model inaccuracies. Okay, just a minute. Yes. So the first thing that we learned was variance stabilizing transformations. Now, what were these variance stabilizing transformations? So we learned that these are some of the transformations which we take into account when the usual Gauss-Markov assumptions fail. So what are the usual assumptions? Usual Gauss-Markov assumptions, they are that the expectation of epsilon would be 0, variance of epsilon would be sigma square I. These were the main two, and x's would be non-stochastic. Those were the usual Gauss-Markov assumptions. Okay, now when this doesn't hold true, that is the constant variance assumption, it doesn't hold true, and we also see something of this sort, that sigma square, that is the error variance, when that uh, is related to some function of the mean of the response. Okay, if or rather not mean of the response, I would say, if that is in some way related to, yes, the mean of the response. So let's say if y is my response variable and we have expectation of y as mu and variance of y as sigma square, and if we find that sigma square is some function of g mu, then in such cases we can take some transformations on y such that these transformations will finally lead to, they will stabilize the variance. Okay, so we have learned a generalized form. So let's say if if we have something like this, so we have the transformation f of y is equal to y to the power 1 minus q by 2 if q is not equal to 2, and log of y if q equal to 2, given that g mu is equal to k mu to the power q. Okay, if g mu is taking this form and sigma square is equal to some sort of is equal to g mu, and g mu takes this form, then we can apply these transformations on our response variable to make the error variance or the prediction variance constant. So then if usual cases are, if sigma square is proportional to mu, then we have our transformation fy as root y. Okay, this is the case when we have a Poisson variable. Okay, now in case we have an exponential variable such that sigma square is proportional to mu square, then we have something like fy equal to log y. So this will hold usually when the variables are exponentially distributed. Okay, if the way if sigma square is such that this is equal to or proportional to mu into 1 minus mu, then we'll have this as sine inverse of root y. So this is usually the case when the underlying y variables follow binomial distribution. Okay, and then we also learned a couple of others, like if we have sigma square which is proportional to mu cube, then we have our transformation as fy equal to y to the power minus half. And again, if we have sigma square proportional to mu to the power 4, we have fy equal to 1 by y, and so on. And this was the generalized formula, y to the power 1 minus q by 2, given g mu takes this form. Okay, so these were some of the uh, transformations that could linearize the model. Okay, we also learned about transformations to linearize the model. So if, let's say, we have a situation where we had something like this, y equal to beta naught e to the power x beta 1, and then if beta 1 is positive, we had a graph of y versus x, something like this, where beta 1 was, let's say, positive. Okay, so if we had something like this, then taking a log transformation of this thing of the right hand side, uh, or rather log y equal to log of beta naught plus beta 1 x, something like this. Okay, so this one solved our problem. So these were some of the transformations that we undertook to correct or rather linearize the model. Again, for example, if we had something like this, okay, where y, this is y and this is x, and the relationship was y equal to x by beta naught x minus beta 1, then a transformation of 1 by y, and this would amount to 1 by y 1 beta naught minus beta 1 1 by x. Okay, so then this transformation regressing 1 by y on 1 by x would give me a linear fit, and so on and so forth. Okay, so we discussed this situation. Now coming back to these things, and we also discussed analytical models, like what to do in case of Poisson, what to do in case of exponential. These things we covered with the help of this generalizable equation. Okay, now this week we learned transformation using generalized and weighted least squares. Now the first thing that we should definitely note is that weighted least squares is actually a special case of generalized least squares. Alright, so this is actually a generalized least square method. Now, what do we mean by generalized least squares? Okay, so usually what did we have? If I write a multivariate multiple linear regression, if we plot a multiple linear regression, we have something like this: y equal to x beta plus epsilon. Okay, this is an n cross 1 matrix, this is n cross p, this is p cross 1, and this is again n cross 1 vector. All right. Okay, so usual assumptions. The number one assumption was expectation of this is 0. Second one was variance of epsilon is equal to sigma square I. And the third one is that so these were the two main assumptions, and if we went ahead for testing, then we took this hypothesis that this followed a normal distribution, okay, with 0 sigma square I. So this assumption came specifically when we went ahead for testing. Otherwise, for estimation, these two and x's being non-stochastic is enough. Okay, so these three enough for estimation, that is to get beta, the estimates of betas. Okay, so what happens, when does generalized least square come into picture? So this happens when to use generalized least squares? Answer is when we don't have sigma square I, when we have variance of epsilon equal to some sigma square v, or rather I would prefer writing it as, okay, I would write it as sigma square v. Okay, so what is v? V is the variance covariance matrix of epsilons. Okay, so v takes this form. Okay, v will have some v11, v12 to v1n, sorry, v22 to vnn. Okay, and we would have v12 to v1n, v21 to v2n, and so on and so forth. Okay, so V ij not necessarily equal to 0 for all I not equal to j. Okay, and Vii is always greater than 0. Okay, alright. So then what and another thing that since this is a variance covariance matrix, V is, we learned, positive definite. Okay, another thing that we learned is, what do we mean by positive definite? So let's say if A is a positive definite matrix, then for all vector y not equal to 0, y transpose ay should be strictly greater than 0. Okay, so until and unless the y vector itself is not 0, y transpose ay is greater than . So if A is a positive definite matrix, then for all y not equal to 0, y transpose ay should be greater than 0. Alright. Now here in this context, V is a positive definite matrix. Alright. Okay. So given that, how do we formulate GLS? Okay, so from here we have seen okay, sorry, yes, where was I? So this is the definition of a positive definite matrix. Again, coming back, okay, so when do we use GLS? So the answer is when there could exist some covariance between the error terms and the variance of each error is not equal. Okay, when the variances of the errors are not equal, then we would get some generalized V, and then we have to see how to implement this V to get our estimates of betas. Alright, now, so in order to do that, how do we do it? We transform y to some gy and x to some gx. Okay, so this is actually a linear transformation. Now once we do that, our model becomes, or rather I would say, if we write this and then if we multiply, so pre-multiply both sides with g. So what do we have then? We have gy equal to gx beta plus g epsilon. Okay, and now for this equation, if we find out variance of g epsilon, that is equal to g sigma square. Sigma square is a scalar, so sigma square will come here. So g v g prime. Now we have to choose g such that, so we'll choose g such that g v g transpose is equal to I. So if we can ensure that this transformation is happening, then equation 2 will revert back, will follow usual Gauss-Markov assumptions, and we can just use OLS to get the values of betas, at the estimates of betas. Okay, so how do we find out? So then this one, if we multiply, then V is actually G inverse into G transpose inverse. Okay, so that implies V inverse is equal to G transpose. Alright, now if this is the case, then what do we have? Then beta hat OLS from equation 2. So from equation 2 we have beta hat OLS, or rather beta hat GLS, because this is transformed. So we will write beta hat GLS is equal to, so that would be x transpose x. So it will be gx transpose gx inverse into x transpose y. Okay, so that would be x transpose g transpose gx inverse x transpose g transpose g y. Okay, so then this would be from here this is actually G transpose G inverse. This we can write as G transpose G inverse, then only this G will come in front. Alright, so here we have G transpose G as x transpose V inverse x inverse x transpose V inverse y. Okay, so this is actually beta at GLS. Okay, and expectation of beta hat GLS is actually equal to expectation of x transpose V inverse x inverse x transpose V inverse y. So that is actually equal to x transpose V inverse x inverse x transpose V inverse expectation of y that is actually X transpose V inverse X inverse, X transpose V inverse. Now expectation of X is X beta plus expectation of epsilon is actually 0. So then this part and this part will cancel and we'll have beta. So beta hat GLS is again unbiased for beta. Okay, and now since we have the this thing expectation, we'll also calculate beta hat GLS. That would be X transpose X inverse into sigma square I. So here we have GX transpose GX inverse into sigma square. So this would be sigma square into X transpose, again G transpose G is V inverse X inverse. Alright, so these are the mean and variance of beta hat. Okay, now the thing is, how do we find out G? Okay, so or rather, how do we find out V inverse? Because V inverse is formulated using G, but from the data there is no way to, we cannot directly formulate what should be V. So how do we get V? So since V is, now the question is how to get V. So since V is positive definite, we can have a decomposition of V where V can be written as something like U transpose lambda inverse U. Okay, where what do we have as lambda? Lambda is a diagonal matrix with lambda 1 to lambda n and off diagonal 0, where these are what? These are eigenvalues of V. Okay, and U is what? U is the corresponding eigenvector. Alright, so this we will have, and then what do? We just have to get V inverse from here. So then V inverse would be actually G transpose G, and from here we can see that G is actually lambda to the power half into U prime inverse. Okay, and lambda to the power half is what? Lambda to the power half is actually lambda to the power lambda 1 to the power half, or like this. This is root over lambda 2, root over lambda n, and 0 over here. Alright, so this is actually what is called the generalized least squares. Okay, and we also learned that the weighted least square is actually a special case where how are the weights assigned? Weights are assigned in such a way such that Wi is proportional to 1 by sigma I square. Okay. So that means variance of epsilon would be something like sigma 1 square, sigma 2 square, sigma n square, and no covariance terms between the errors. Okay. So in such a case, G would be so in that case, first let us find out what will be beta hat. So beta hat GLS would be X transpose V inverse X inverse X transpose V inverse Y. Now since this is V inverse would be actually W, because Wi's are proportional to 1 by sigma I square. Okay, so we'll substitute this V inverse with W. This will be X transpose WX inverse X transpose WY, and variance of beta weighted least squares, I would rather write here weighted, would be X transpose WX inverse into sigma square, or no sigma square, because that is being taken into account by this W matrix. Okay. Apart from this, we also learnt some other sorts of transformation, which is the Box-Cox transformation. Okay, now this is actually a power transformation. All right, now what is the transformation? How does it look like? It looks like this: W equal to y to the power lambda minus 1 by lambda if lambda not equal to 0, and log of y if lambda equal to 0. Okay, this is another specially useful class of transformations, but it comes with its own set of disadvantage. The first disadvantage being that if lambda tends to 0, then this one will W will tend to, then this y to the power lambda will tend to 1. So then the variation in y would absolutely disappear if I mean will gradually disappear as we move lambda towards 0. Okay, so that is something we have to be very mindful of. And then if lambda is equal to 0 actually, then we can use this log transformation. This log transformation is actually pretty common, and you might find yourself making this transformation very often in practical situations to do away with model inaccuracies. Okay, other model assumption inaccuracy. Okay, but another disadvantage of this function, of using this function, is that if lambda is too large, okay, this case was lambda is too small, lambda is too small. Then we have this problem. On the contrary, if lambda is too large, then W will also be very, very large. W okay. So in case W is very, very large, then this function will also change quite rapidly. So then what do? We use some sort of normalization factor, and we use what as a normalization factor? Usually we use the geometric mean. So then W star would be something like this: y to the power lambda minus 1 by lambda into GM y, that is geometric mean of y, to the power lambda minus 1 for lambda not equal to 0, and again gmy into log y if lambda equal to 0. Alright. Now how do we go ahead with estimation? So in order to proceed with estimation, we transform from y1, y2, yn to w1 star, w2 star to wn star. Okay, and then we instead of y we fit w star on x beta plus epsilon. Okay, so we choose, first step is we choose a lambda, second step is we transform y to w star, and third step is we fit this. Okay, now the question is how to choose lambda. So now the question becomes how to choose lambda. So what do? We choose lambda between -2 and 2. Okay, and we can also take an extended range if necessary, but usually we take lambda from -2 to 2, and at each lambda what do? We calculate, we fit this thing. Okay, we fit this model and calculate SS residual of the model under that specified lambda. Okay, and the maximum likelihood estimate of lambda is that lambda where SS residual is minimum. Okay, so this is some sort of an approach that we consider in order to estimate the value of lambda. All right. Fine. So given these things, in the last 2 weeks we learned how to get how to get around the problem of non um, non-constant variance, and use different techniques to circumvent the problem of non-constant variance. Okay, so the first things that we learned was, okay, we could apply some sort of analytical transformations. Sorry, if we know the distribution of the predictor, then apply some sort of known transformations. If we know the relationship between the variance and the expected value of the response, then choose a different set of I mean choose a different set of transformations, or simply look at the relationship between the predictor and the response variable, and based on their relationship on the graph, try to find out what sort of a relationship do they have in between themselves. And also, if we are very sure that there exists some sort of problems or some unequal variance between errors do exist, then we can go ahead and fit the uh, generalized least squares method. We can use the generalized least squares method to account for that difference in individual error variance, incorporate that in the model, and then proceed to uh, do our analysis or get the estimates of betas. Okay, and also we found that uh, another there exists another class of transformation, which is the Box-Cox transformation. Okay, and we fit we try to select lambda, suitable value of lambda, by iterating over a range of lambda and choosing that transformed model which gives us the minimum SS residual value. Okay, so these were a few things that we learned during week 9 lectures. Now, another thing that I would want to touch upon is when to use what sort of transformation. Okay, so this might not hold true always, but usually it does. Okay, so here are some guidelines. Okay, so if we see that if we somehow see that mu is not mu is actually expectation of y. So if we see that mu is not a linear function of the predictors, then what do? We usually transform the response and or the predictor. Okay. The second scenario is if we find that there are unequal error variances, then what can we do? We can either transform the response and or predictors and fit OLS, or we could fit weighted least squares. Okay, so as a general guideline, it is said that if we transform the response variable, then problems associated with the error terms epsilons, those usually go away. Okay, it may help with nonlinearity, but if we find nonlinearity in the residual plot, then we could go ahead and make some transformations on the predictors as well. Okay, so with that, let us try to solve a few problems based on today's class. So let us see this one. So this is a model y1 equal to delta naught, xi1 to the power delta 1, xi2 to the power delta 2. So can this be linearized? So if we take log of y1, we'll have log of delta naught plus delta 1 log of xi1 plus delta 2 log of xi2. So now this one, if we consider it as delta naught star, then this and this, it is a linear model. Okay, because it is linear with respect to the parameters, and then this one forms a good LM model. Okay, this is actually transformed after log transform to a multiple linear regression. Okay, so therefore this can definitely be linearized, and that's the answer. Okay, moving on. This is, can the model y equal to beta naught x by beta naught 1 plus x be linearized? So let us find out. If we take 1 by y, then we have beta 1 plus x by beta naught x. So that would be beta 1 by beta naught into 1 by x plus 1 by beta naught. Okay, so if we fit 1 by y on, if we regress 1 by y on 1 by x, then we would be easily, we can easily recover estimates of 1 by beta naught and beta 1 by beta naught. So using this one, plugging it here, we can get estimates of beta 1 hat and beta naught hat. Okay, so can the model be linearized? Yes, the model can be linearized, and that's the answer. Alright, moving on. Suppose we want to fit the no intercept model yi equal to beta xi plus epsilon I using weighted least squares. Assume that observations are independent but sigma I square equal to variance of yi equal to k xi square, that is variance of yi is proportional to square of corresponding xi, then what will be the least square estimate of beta? Okay, now how do we get the weighted least square estimate? We just minimize the wi ei square. So here what do we have? Wi ei is what? Ei is actually yi minus beta hat xi whole square. Okay, so this is actually sum of squares due to residuals. Now differentiating with respect to beta hat s is residual and equating it to 0 leads to summation 2 yi minus beta hat xi into, this is actually minus xi yi. Okay, and we equate it to 0. So given then that would be summation xi yi wi equal to okay, so we don't need this minus sign. So this one equal to beta hat summation xi square wi. So then we have from here beta hat gls as summation xi yi wi by summation xi square yi, so wi. Now here we know that wi is actually proportional to 1 by sigma I square, right? So then here what do we have? Sigma I square is equal to k xi square. Okay, so wi is equal to some k star by sigma I square is how much? Sigma I square is k xi square. So it would be k star xi square. So plugging it here, what do we have? We have beta hat equal to summation xi yi wi by summation xi square wi. Okay, so wi is this thing, so we'll put it here. We'll have summation xi yi wi is k star by xi square by summation xi square into 1 k star by xi square. So this k star will cancel. This xi square and this xi square will also cancel, and this one will cancel with 1. So ultimately we are left with summation I 1 by n summation yi by xi, and that is our answer. Alright. Similarly, From here, if we want to find out the expected value of beta hat, then what do? Then we just find out expectation of beta hat GLS, and we always remember that y equal to x beta plus epsilon, where the model is such that expectation of y equal to 0, but variance of y is equal to is not equal to it is always greater than 0 and equal to some v. Alright, so we'll have to do this, that expectation of summation yi by xi by n, so this would be 1 by n summation expectation of yi by xi, so this would be 1 by n summation 1 by xi. Expectation of yi will be xi beta plus epsilon, expectation of epsilon I is 0, so this cancels, so we'll finally arrive at beta. Okay, so moving on to the next one. So again, variance of beta hat is the same thing. We have the formula for beta hat 1 by n summation yi by xi. So now we just have to find out variance of beta 1 hat, and that would be 1 by n into summation 1 by xi square variance of yi. There will be no covariance term. Covariance yi yj equal to 0, because here it is mentioned in that way. This is actually observations are independent. So whenever observations are independent, here they are written, observations are independent. Okay, so whenever observations are independent, then under this criteria variance of summation yi is equal to summation of variance of yi. But if dependent, then we have to write variance of summation yi equal to summation of variance yi plus double summation I not equal to j covariance of yi yj. Okay, so this term will become 0 because it is explicitly mentioned that our observations are independent. Alright, so now we just have to plug in the values and find out how much is the variance of beta hat. Similarly, we'll have this thing. Okay, so if, okay, now this question says when Vy sigma square is proportional to Ey, which of the following is a useful variance stabilizing transformation? So you just have to use that sigma square equal to g mu, get the form of y, fy, okay, where g mu is some k mu to the power q. So based on q equal to 1, we'll have to find out what will be the value of fy. Okay, okay, this question also says that we have some variables which follow exponential we are considering this one, what is the reasonable choice of fi. So for exponential, we've already seen which is a reasonable choice, so you'll have to fill it up. And similarly, if it's a Poisson variable, then also we'll have to fill up our reasonable choice. Alright. Now, once these things are sort of acceptable and clear, let me just solve a few real life problems that will help you understand, or rather carry out analysis, okay, in the real world scenario. Okay. um all right. So let me just move on to that. So before that, I'm going to stop presenting. Okay, fine. So let us see this example. Okay, we have 13 time periods. Okay, and we are trying to measure uh, the time between learning and recall and percentage of correct recall. So what we are actually studying is that how much time is required between learning something and then remembering it or recalling it, and the percentage of correct recall. So what we are interested to see is that if the time given between learning and recall is less, do we have more percentage of correct recall or do we have less, or is or are these two completely not associated or not related at all? Okay, so in order to do that, let us just go to our R console, and this is my data set 1. So I have entered time in a vector and proportion in another vector. So this is my time is actually my x, and proportion, percentage of correct recall, this is my y. Alright, now first things first, let us plot a scatter plot and see the relationship between x and y. So to do that, the simplest command in R is plot. So plot time comma prop will actually give me the relationship between this and this. Okay, so here we see this is actually the relationship between this variable and this variable. Okay, so from here we can see this doesn't look like a straightforward linear relationship, so maybe some sort of transformation is needed. So from the first at a first glance, this is my comment. Okay, now before even proceeding, let us first fit one linear regression to this and let us see what happens. So if I want solid colors, so I want this. Okay, and I want to fit a linear model. So let's say model linear, I am going to name it, equal to lm of proportion on time. Okay, so this is my linear model. I fit this, and then I want to overline this regression line on this scatter plot to see how well is it fitting. I'll make it into a separate color. Let me make it blue. So now if you see, this is actually the linear regression fit. Okay, now from here itself we can see that the fit doesn't look nice. Okay, but still let me find out if the residual, how does the residual plot look like. So to draw the residual plot, here we can do something. Actually, there is a command which will automatically give us some important plots related to any linear model. Okay, so we'll go ahead and use that function to see and visualize 2-3 plots together. Okay, so before that I want to partition this frame into 4 parts. So let me just do this. I am going to write I'm setting margin, and then I'm going to split it into 4 windows. So this part is optional, you could do it, you could skip it. And then the thing that I need is, if I plot my linear, or rather model linear, so see, if I plot my model linear, then I am getting a plot like this. Okay, now if we look closely into this residual plot, this one clearly shows some sort of nonlinear pattern. Okay, this doesn't look randomly scattered about 0, and some sort of nonlinearity is seen in this residual versus fitted graph as well. So if we transform this variable excuse me Sorry for the interruption. So, as I was saying, okay, so as I was saying, so from the residual versus fitted plot, it is evident that there exists sufficient non-linearity in the data. Okay, so coming back here, this is residuals versus fitted. So if so from this plot that we have over here, you see that smaller values of time are clustered together and then distant values are apart. So for this non-normal thing, first let us try to find out what happens if we take a log transform of the x values, that is log transform of time. So let us just take, I will name it as model 2, or rather let me first plot. If we plot, instead of time, I'm going to plot log of time against prop. So see, if I give up our new command over here, or let's say this thing, this is how log time on x-axis and prop on y-axis is looking like. Okay, now if I want to add there, if I want to fit that linear regression model, what is the command that I should use? I am going to use this thing, model 2 equal to lm, let's say I write prop on a log of time. Okay, this is my model 2 and I overlay this thing on the existing plot. So abline model 2 and then color equal to, let's say, something green. Okay, so now you see this plot is better. So after transformation, this is the plot that we get. Okay, and this plot is better in the sense, so this one is actually here we have prop, here on the y-axis we have prop and here we have log time. Okay, in the previous one what did we have? We had proportion and time, but here we are having proportion and log time, and we see that this is sort of well explained by the linear regression. Now if we want to plot the residual plot, I am going to give plot model 2. I'll clear this, then fit these together. Now if we see, Now if we consider the residual plot and those things, we'll see that these residual plots are better. Okay, it seems to be randomly scattered around 0.04. So again I'm going to remove this and I'll just plot this thing. So this is actually how my residuals versus fitted plot is coming around. Okay. So this one shows better so this residual versus fitted is actually better than this residual because this is indicative of a clear pattern. But here residual versus fitted, they are fluctuating about 0, even though there still exists some sort of pattern. This looks like this is better than the previous one. Okay, now if we want to test whether if we want to see what happens when we transform both, okay, when we transform both the phenotypes, so what do we have to do then? We have to plot log of prop on log of time. But see, okay, these are QQ plots which are coming, but this plot is also not a straight line. Okay, so this one seems like a better fit. This proportion, the response regressed on log of time. Okay, and we had the model like this. This was the residual versus fitted. This is the QQ plot, which shows that since these points all fall on the y equal to x line, then it caters to the fact that the residuals are normally distributed. This look like they are normally distributed. We could also test if the residuals are normally distributed to test whether residuals are normally distributed. We could use the Shapiro-Wilk test. So how do we do that? We find out, we write Shapiro dot test and we give that residual value. So it would be resid of model 2. Okay, and the null hypothesis of Shapiro-Wilk test is that it is normal. Okay, so here since p value is 0.5936, therefore we conclude that there is, since p since p is greater than 0.05, here in Shapiro-Wilk's test, H naught is that distribution is normal. H0 corresponds to the fact that distribution of residuals of model 2, that is proportion on log time, is normally distributed. Okay. Alright, so now since this model is giving us a better fit of the data, what can we do with it? Okay, we can see some sort of improvement. Now let us compare the fit of both the models. So if I see this thing model linear, if I run it, I get this and this. So if I do a summary of model linear and summary of model linear, then we get this output. Okay, this is the estimate standard error, this is the intercept term, this is the time, and we have adjusted R square and F statistic and p value, and we have the residual standard error. Okay, and if we go and do a same thing, summary of model 2, we also get similar things, multiple R square, adjusted R square, and then residual standard error, and so on. So the thing that we are most interested in, and what we want is lower R square or higher R square or adjusted R square for model fit, and we want the F statistic to be significant. So here we see this is also significant, but this is highly significant, and the adjusted R square value has increased quite a lot. Okay, we could also, since we are not including or excluding more regressors, since the number of regressor remains fixed at 1, we instead of comparing adjusted R square, we could also compare these multiple R square values. Okay, so then this is actually 57%. So this model where we did not make any transformation, the variable time was only able to explain 57% of the total variation in that proportion of correct recall. But after transformation, we have fit the model so well that this predictor time is now able to explain 98.99% of variation in the responses or in the recall time. Okay, so this is of course way better a fit than the previous one. Okay, now if we come to some research questions that we can answer from here, let us see what sort of research questions can we answer. So here they are saying, is there an association between time since memorized and effectiveness of recall? So to see whether this is actually our final model. So I'm just going to keep it here. Okay, so now from here we see if there is an association between time since memorized and effectiveness of recall. So time since memorized is this thing, log time, and effectiveness of recall is proportion. So what it actually is wanting is that we have fit a model like this, y equal to beta naught plus beta 1 x1, where x is log time and y is the effectiveness metric, which is nothing but proportion of correct recall. Alright, now we want to test whether this x is having any effect on y. So our h naught is actually beta 1 equal to 0 versus beta 1 not equal to 0. So this is actually a t-test that we have learned. And what is the test statistic? It is actually beta hat by standard error of beta hat. So from here we can see the t value is 59.63 and p value is this thing, which is way less than 0.05. Therefore, what do we say? That, so the conclusion is yes, there is an association because of this low p value. Is it okay? Fine. The next question says, what is the expected proportion of words in a randomly selected person would recall after 1000 minutes? Okay, so what is the expected proportion of words? So what are we looking at? We are trying to get a prediction. We are trying to predict if x equal to log of 1000, then how much will be my y? Y will be how much? Okay, so in order to do this, we can use this predict command. So how do we use this predict command? We can write here predict dot lm of, here we'll write model 2 new data equal to, okay, data dot frame time equal to 1000. This will give us a point estimate, that is 29.9. okay, and if we want a prediction interval around this estimate, then we have to give here interval equal to prediction. So this will give us a prediction interval, that how much can the expected y range, I mean where can the expected y range. So this is the lower part, this is the upper part, and this is the fitted point estimate. Okay, so how do we actually interpret this thing? So if we have something like this, then we say that so this the prediction interval that we get is usually a 95% prediction interval. So this one, it mentions that a randomly selected person will, so we are 95% confident that a randomly selected person recalls approximately 29.9% or 24.5 to 35.3% of the words after 1000 minutes. All right. Okay. Moving on to the next question. So if we have something like this, how much does the expected recall change if time increases tenfold? Okay. So expected y, the model is y equal to beta naught plus beta 1 log time. Okay. So tenfold increase in time means what is the effect this variable is going to have on y. So that is actually beta 1 into log 10. Okay, so the mean response is going to change by this thing, right? So then the answer is actually, we have beta 1 from here as minus 0.079. So this would be minus 0.079 into log 10. That would be something close to minus 0.182. So how do we interpret this? The interpretation will be that we expect (18.2% decrease in recall if time increases tenfold. Okay. All right. Now the thing is, this is actually something which we expect. If I am asked to memorize something and right now I am asked to recall it. Suppose you give me a page of a list of words, you ask me to read it twice, thrice, and then after 2 minutes you ask me what were the number of words that was written over there. I will be able to tell you easily. But if you ask me the same question and the same if you ask me the same question after a certain time has elapsed, okay, let's say if you ask me this after 1 hour, that what were the words that you saw in that list, chances are that I will not be able to recall as many as I would have when I was recalling immediately. So delayed recall is usually less than immediate recall. Okay, if I tell somebody to do something today, maybe they'll remember, if I don't follow up, chances are that if this task has to be done after 20 days, chances are people might forget. Okay, so that's the thing. So here, from here, what we see, that as time is increasing, proportion of recall is actually decreasing. So this is something which we would expect. All right, so just to give an intuition of how to determine or how to assess intuitively whether you are moving in a correct direction or not. And even if you are not moving in the correct direction, if you don't think you're moving in the correct direction, maybe you are venturing into something new, and that could also be explored. So just a heads up on that. Okay, so yeah, this is how you would calculate or transform variables, make transformations on the variable. All right, all right, now let's move on to a similar problem, but this one. Okay, so here we have 70 data points where we are comparing diameter of a tree with volume. Okay, so in this example, we compare diameter of a tree with volume. So I'm going to load this data set into my workspace, and then, as with every other thing, I'm going to do a plot. So I'm going to do a plot of see, so v1 and v2, I'm going to give a header equal to true. Okay, yeah, so this would be diam, and this is, let's say, wall. Okay, so volume versus diameter, this looks something like this. All right, here again we see non-linearity in the data set. All right, this is the raw data set. Now what is the nature of association? If we plot, same thing, if we just do a linear model, let's say model 3 equal to lm wall on diam, because volume depends on diameter, and data equal to short leaf, and then I do a abline of this thing, model 3 color equal to purple, let's say. Okay, so from here we see this is our linear regression plot. Doesn't look like that the linear plot is making any sense here. Okay, So given that this is not making any sense, or rather it's not giving a good fit, we'll see what happens if we transform the x variables and if we transform the y variables. Okay, so before going that, let us first take a look at the residual plot. So if I do a plot of model 3, see, this is the residual plot. Now from the residual plot, residual versus fitted plot, so from here we see as this fitted value increase, so we see that as this fitted value increase, the residual variance seem to increase. Okay, so there is this funneled sort of a shape, and there seems to be some sort of non-linearity in the data. Okay, so when the case arises that this is this is non-linear, or variances are not equal, or normality criteria is not satisfied. So if we look at the QQ plot, here in the QQ plot also we see that doesn't look normal. Okay, so this one also deviated from normal. I could write this as deviation from normal. Okay, so when we have situation where error variance are not constant, okay, there seems to be a non-linear pattern in EI versus YI hat, and EIs or the distribution of EI or the epsilon i's or EI's errors, I would write here errors are not normal. Then what is the way out? Then what usually is done is that we transform both x and y. Okay, so let us do a log x and log y and then find out what is happening. So if we do a log x and log y over here, if we plot, instead of this thing, we plot log of this thing versus log of this thing. Okay, See, now using this log-log transformation, this one looks like that this has become a little straight. I mean, the linear relationship is now a little bit visible. Okay, so if I fit model 4 as lm log of vol on log of diam data equal to short leaf. Okay, and then if I just superimpose this line on the plot, okay, so if I do this, then after this fitting we have a plot like this. Now this one seems to fit the regression well. Alright, so now let me just take a look at the summaries for these two. So summary model 3 and summary model 4. Okay, so now if we compare the two summaries, here we see for this one we had an adjusted R square or an R square of 0.89, but here when we are making this log-log transformation, then we see multiple R square increases from 89 to 92%. Okay, so after this transformation we see, yes, so after transformation we see that R square changes from 89 to 97%, which is actually a significant increase. Okay, now let us look at the residual figures. So if I go here and if I write plot of model 4, this is how the residual plot looks like. Okay, so now from here we can see that scattered so from here we see that it is scattered about 0 and no pattern, looks random, and variance also in check, no pattern, no funnel shaped. Okay, no funnel shape is observed. Excuse me. So all these points confirm that this model has fit the data well, and we can finally go ahead with this model. Okay, so now that we have our model in place, how do we answer our research questions? So the question was, what is the nature of association between diameter and volume? So here, if this is my model, so nature of association is positive linear association, because beta is positive, this one. Okay, okay. Also, from the residual plot we had this, we should also check the normality of this the residuals. So if I plot plot model 4, if I do press enter, then I have the standardized residuals versus fitted values, residual versus leverage. Oh, okay, where is the QQ plot? Okay, residual versus fitted, this is the QQ plot. Okay, so from QQ plot we see that situation has improved. Okay, looks normal. Now how do I ascertain whether it is normal or not? I'm going to do a Shapiro test, Shapiro.test, and then I'm going to test resid of model 4. Okay, so Shapiro test of residuals is giving me this thing, which shows that these are normally distributed. So we are good to go ahead with this model. All right, now here if I come, nature of association, I have said this is a positive linear association. All right, now so this says that as the log of the diameter increases, the log of tree volume also increases. Okay, now since it's an increasing function, we can just simply say that as diameter increases, volume also increases. Okay, now the second question is there any association between diameter and volume of short-lived pines? Okay, is there any association means, is the association significant? So we see that the p-value is less than 0.05. So yes, association is significant. All right, and then the final question is, what is the expected change in volume for a two-fold increase in diameter? Okay, so the model is actually this thing. This is log y equal to beta naught plus beta 1 log x. Okay, so 1-fold increase or 10-fold increase in predictor x means this would become 2x. Okay. So we can write this as log y equal to beta naught plus log of x to the power beta 1. Okay. Now this is one model. Second is log of y star equal to beta naught plus log of 2x to the power beta 1. Okay. So if I subtract, then we have log of y by y prime equal to log of 2 to the power beta 1 or that would be 2x 2 to the power beta 1 or it would be x to the power beta 1 this would be x to the power beta 1 by 2x to the power beta 1. So that would be half. So y by y star will be 1 by 2 to the power beta 1. So y star will be 2 to the power beta 1 into y. Okay. So what will be the, how much will the y increase? It will increase by 2 to the power beta 1 fold. Okay. So then the interpretation will be that 2-fold increase in x leads to 2 to the power beta 1 fold increase in y. Okay. So what will be the estimate? Estimate would be 2 to the power beta 1 half beta 1 hat. So beta 1 hat will get from here 2.25. So that would be, answer is 2 to the power 2.25, and that whatever that is our final answer. Okay. So whenever we have these scenarios, these are some guidelines. Whenever we have a situation where the error variances are not constant and there seems to be non-linearity and errors are not normal, it is usually preferred to go for a transformation for both x's and y's. Okay. And if we find that only and if we find that non-linearity and normality is violated, then we could try transforming y we could do that based on some variable so sorry, not non-linearity. Whenever we find that the homoscedasticity assumption and normality assumption is violated, usually we will transform y. And if we see that there is non-linear pattern, we would first transform x and or y. Okay. All right. So with that, I am going to close today's session and I'm going to see you next week.